Editor-in-Chief of ACS Nano. We have quite a program for you today on nanotechnology and medicine and fighting COVID-19. Our first speaker will be Professor Paula Hammond of MIT. Then we'll have a panel, and then Professor Andre Nell, my colleague here at UCLA, and we'll wrap up with a short presentation from Professor S.K. Ramesh from Cal State Northridge, who's one of the candidates for IEEE president. We have quite a program for you, and we're looking forward to enjoying that with you. As always, thanks to Alice Zhang, who's put this entire set of lectures and program together. And I also want to thank Chuanchen Zhao, my student up very early here at 5 in the morning in Los Angeles to help me on the technical side. So thank you very much. It's my great pleasure to introduce my friend and colleague, Paula Hammond. Professor Paula Hammond's the David H. Koch Professor and the head of the Chemical Engineering Department at MIT. She's one of the few people elected to all 3 US academies, the National Academies of Science, Engineering, and Medicine. She's also one of our original 4 ACS Nano editors. She's famous for her work in layer-by-layer assembly of polymers, now focusing on nanomedicine, as we're going to hear today. Paula, the stage is yours.
Thank you. Thank you, Paul. I'm really excited to have a chance to speak today. I'm going to be focusing on nanoparticles and nanomedicine for cancer and for other diseases, but I think that the principles will translate to several areas of health. Now, the technique that we use in our lab is a very simple one that's based on electrostatics. We use a simple method known as layer-by-layer assembly, and this assembly method is actually one that allows us to generate extremely thin films by alternating positively and negatively charged species. And as you can see, you can start with a simple dilute water solution that contains a polycation, a multiply charged polymer, and you immerse a substrate that is oppositely charged. The polycation will adsorb until ultimately you reverse the surface charge. At that point, you rinse the substrate and then immerse into another dilute aqueous solution. In this case, you can generate a second film, and in alternation, plus and then minus, plus and then minus, you can build up a multi-layered thin film. You can use a number of different interactions to construct these films, and this provides us the opportunity to incorporate a range of different systems. Now, it turns out that because this is a water-based assembly method, we can actually use a method that is very kind to the use of these systems. Biological materials in particular are sensitive to heat, they're sensitive to solvent, and we'd like to avoid exposing them to those conditions. Now, we can use layer by layer to address the coating of large-scale biomedical devices, but we can also coat very small things using electrostatic assembly. For example, we can utilize a simple liposome as a solid core and then coat that surface with a positively charged material, for example, a degradable polymer or a polymer that can be used to help escape the endosome when we deliver our drug. We can then incorporate a negatively charged material and then a positively charged one. And in our case, we're very interested in addressing cancer by using a 1-2 punch, by incorporating a small molecule chemotherapy drug in the core of our nanoparticle, which can be a liposome or can be a polymeric degradable nanoparticle. We can then incorporate on the surface of that nanoparticle a negatively charged siRNA or DNA or a range of other nucleic acids sandwiched between 2 positively charged layers. This protects the nucleic acid and allows us to deliver siRNA that can block the defense mechanisms of the tumor that make it resistant to the chemotherapy drug. Finally, we have this outer layer, and this outer layer is actually very effective in enabling us to prevent absorption of proteins in the bloodstream and enables us to target the nanoparticle to a specific part of the body, in our case, the tumor. The size of these nanoparticles is around the range of 100 to 120 nanometers, and that allows us to take advantage of some aspects of cancer to get into tumors. So all of this involves combining engineering and physical chemistry, design, understanding biology, and medicine. And we have clinical and biological collaborators that help us with this work. Now, these layer by layer nanoparticles can be constructed on any core. A liposome is very convenient for us because we can use it to contain a drug that is soluble in the aqueous phase. For example, we can encapsulate a range of different drugs. Here we have an uncoated liposome. These are FDA approved. We can design them so that they exhibit a negative charge, and then we can introduce our layers, and we get these LBL-coated liposomes. Both of these are viewed in cryo-EM. We can also coat solid polymeric cores, such as polylactic glycolic acid, or PLGA. And this gives us a huge amount of flexibility with respect to what we can incorporate into these material systems. I think of this very much as like that candy-shelled material that's called a Wonka gobstopper or a jawbreaker. It has different layers of sugar or candy that get released at different times. In our case, we are releasing the siRNA early in the process to silence the defense mechanism, and then releasing the chemotherapy drug, which can then more effectively kill the tumor cell. So this modular design allows us to get enhanced accumulation in solid tumors. Many believe that this is due to the fact that solid tumors may grow rapidly and that the blood vessels that are generated may have leaks or defects in them that allow these nanoparticles to circulate and accumulate in the tumor. I think of it very much like the pinball game, in which you have a metal ball that gets lifted up and gets caught in all of these passages. We have an opportunity for a nanoparticle that is streaming along a blood vessel to get into the interior of a tumor and to spend time within that tumor interacting with other cells before it encounters another opportunity to exit through a second leak in the blood vessels. This is often referred to as the EPR effect. However, it is also known that the EPR effect may not be present in a number of human tumors. So we do need other ways to get across the blood vessel walls of tumors. And this includes understanding how we can get these nanoparticles across the blood vessel walls, and how we can also, once inside the tumor tissue, get desired uptake by tumor cells. So we try to rely on a means of several mechanisms to get into tumors. So as I mentioned before, this is a modular design, and it allows us to use the outer layers as targeting systems. However, what's really interesting about layer by layer is that because you have a polyacid and a polybase layered together, a number of our nanoparticles can exhibit an isoelectric point, which means that we can assemble a layer by layer nanoparticle so that it has a strong negative charge at physiological pH. However, if it gets into the tumor hypoxic environment, which has a slightly lower pH, we can actually shift the charge of that nanoparticle from being very highly negatively charged to being weakly charged or even positively charged. And that leads to a nanoparticle that interacts strongly with the tumor cells that are present. So we have a nanoparticle that is non-interactive with cells in the bloodstream, but is highly interactive with cells when it hits the tumor compartment. We also note that as we go to lower pHs, we can get swelling of these layers because we are protonating the negative charges on that backbone. and that leads to erasing the ionic crosslinks that hold the layer by layer film together. So we begin to see swelling, and this leads to release of the siRNA that we ultimately see. This is actually advantageous because the endosomal pH is slightly acidic. It actually goes down to pH 5. This outer layer is interesting to us because it presents an opportunity for targeting, as I mentioned before. And we can actually choose a polyelectrolyte that is an intrinsic targeting vehicle. For example, hyaluronic acid binds specifically to the CD44 receptor, which is highly overexpressed in a large number of solid tumor epithelial cells. So if we look at this outer layer, if we use hyaluronic acid, we can have multiple advantages. It's strongly negatively charged, and it has a high degree of hydration. And this makes it the ultimate stealth outer layer, which means that when it goes through the bloodstream, it's not very easily recognized by other cells such as monocytes, and it's weakly interactive with these cells. This means that we have a longer circulation half-time over which the nanoparticle has the opportunity to accumulate ultimately in the tumor. This long plasma half-life is helpful, but it also turns out that hyaluronic acid is able to, once it is in the tumor, bind specifically to ovarian cancer tumor cells, triple-negative breast cancer tumor cells, and a range of other tumor cell types. And this allows us to have a molecular targeting that is much more focused, and we can get selective uptake by these cancer cells. We can see in this image here, nanoparticles that have accumulated within the cell of a tumor cell. These are triple-negative breast cancer cells. If we introduce a huge excess of hyaluronic acid, we can greatly decrease that binding and interaction, proving that this is driven by the binding of HA to CD44. We can also look at a tumor section, and in this tumor section, we have tail vein injected nanoparticles into a mouse that has a tumor. When we look at the tumor, we can stain for the nanoparticles, which show up as green, and the CD44 receptor, which shows up as red. And we can see that these are co-located. We also see that there are a number of cells here. We can see the blue nuclei of. These are stromal cells. They're not tumorigenic, but they surround the tumor. And we see that our nanoparticles are able to penetrate that stroma and get into the core of the tumor. So we have multiple ways of targeting using these nanoparticles. We use nanoparticle size to help us with accumulation in the tumor. We have the microenvironment of the tumor, including tumor hypoxia, which gives us a slightly lower pH and a way to trigger these nanoparticles to become more interactive with cells. And we have very specific targeting of the cell receptor CD44 through binding, such as the hyaluronic acid CD44 binding. We actually looked at a model of these systems using non-small cell lung cancer, which is an extremely aggressive form of cancer. This cancer is actually one of the leading causes of cancer death worldwide. About 85% of all lung cancer cases are non-small cell lung cancer. There are frequent mutations that show up in this form of cancer. One of them is an oncogene known as KRAS. KRAS is typically thought of as undruggable by small molecules, and therefore using siRNA to silence this gene can be highly effective. On the other hand, we can also try to address the p53 gene. This gene is a guardian gene that typically monitors for the presence of DNA damage. However, when it is lost in cancer, which is a common mutation that occurs, you lose that monitoring and you have an opportunity for cancer cells to thrive. So to restore that p53 function, we introduce a microRNA known as miR34. We can combine the KRAS siRNA and the miR34A in the adsorption of our film. So here our blue layer of nucleic acids will contain both of these. We're using polyl-arginine for the positively charged polyelectrolyte. Polyl-arginine has been shown to aid in endosomal escape of the nanoparticle. And ultimately, we have hyaluronic acid as our CD44 targeting outer layer. And we can see from the release that we get a very rapid release of siRNA and a slower release of the chemotherapy drug, in this case, cisplatin, which is embedded in the liposome. So we get that stagger that we want, with siRNA being released early enough to silence all of these defense mechanisms of the tumor, and then the cisplatin released at a later time. When we look at mouse models, we can compare the accumulation of our nanoparticle in healthy mice with the accumulation of the nanoparticle in mice that have this non-small cell lung cancer in their lungs. And what we find is that there's a very strong difference in where these nanoparticles accumulate. For example, when we look at the lungs of these two sets of animals, we can see that the cancered mice have a lot of accumulation in the lung, which is where these cancer nodules exist. And we can stain the tissue of these animals and find that those tumor lungs have a very significant amount of CD44 expression, which we think explains this huge increase, as we can see here, in the accumulation of the nanoparticle in the lung. We can look at how effective we can be in treating non-small cell lung cancer. And in this case, we're using a modified cell line that was developed in the Tyler Jacks lab at the Koch Institute. This provides us with a very realistic picture of an aggressive form of non-small cell lung cancer. And what we find is that when we compare the control with our nanoparticles, we can see some very real differences. Here, what we can see is that we have a very significant decrease in the size of the tumor when we compare the combination treatment pre and post to the actual control. We can also see that there's an increase in the survivability of these animals by about 30% compared to animals that were treated with just the cisplatin alone. And we can see this also in the fold change in the tumor volume, with the tumor volume being much smaller in the combination treatment than in the treatment with cisplatin or with RNA alone, indicating that these kinds of combinations can be very powerful for treatment of cancer. We're really interested in how we can modify these nanoparticles so that they are effective against a range of different cancer types. So in our studies, we began to use a method of rapid assembly of these nanoparticles so that we could create libraries of them. And in making these libraries, we were able to explore a much broader range of outer layer chemistries, with the idea that we may be able to discover additional polyelectrolyte outer layers beyond hyaluronic acid that would allow us to target nanoparticles to ovarian cancer, which we were particularly interested in because of the challenges that we face with ovarian cancer, which has had no improvement in cure over the past 50 to 60 years. So we looked at a range of different outer layers. Some of them were synthetic polypeptides, and some of them were naturally occurring polysaccharides. And we used a robotic assembly process to do that work. We found that we could actually observe a huge increase in nanoparticle accumulation for some of our nanoparticle types when we compared their association with 10 ovarian cancer cell lines against 7 non-cancerous cell lines. When we finished our study, we found that along with hyaluronic acid, there were at least 2 new polyelectrolytes that we had not expected that showed a high amount of accumulation on ovarian cancer cells. And these were poly-L-glutamic acid and poly-L-aspartic acid in this multilayer form. And this was surprising to us because we didn't know of any specific binding partner for these polyelectrolytes with ovarian cancer cells. We began to study how these nanoparticles accumulate and co-localize with tumors when we do animal studies. And we found that in ovarian cancer, we could inject via the intraperitoneal cavity or the abdominal cavity, and we could use an intravenous or IV injection. IP and IB both gave us very faithful accumulation of the nanoparticles in the regions where we have the tumor, and we can see this with the infrared signal overlapping the tumor. However, the signal between IP and IB were quite different. We would see typically about 5% accumulation with IV. However, we could see a much larger degree of accumulation with the IP injection. In fact, what we found was 80 to 90% recovery of the nanoparticle fluorescence in the tumor compared to the other organs with IP injection, which indicates that the mode of administration, as well as this outer layer, can greatly increase the efficacy of these treatments. We found that for our systems, we had a very long time retention. And this time retention essentially gave us a period of up to 72 hours where we had greater than 50% fluorescence in the tumor. This is very different from what we see with PEG, or polyethylene glycol, in which this black bar here indicates that we have much more in the spleen than in the tumor, even at 24 hours. And again, comparing these carboxylated nanoparticles and their residence time in the tumor, much longer than what we see with polyethylene glycol when we're looking at the 24 to 72 hour period, which is the period of release for these nanoparticles. We also found that these nanoparticles did give us significant penetration into tumors. All of them extend over 100 microns into these tumors, which is a fairly effective degree of penetration. We found that hyaluronic acid was particularly good at tissue penetration, getting us closer to 200. But we also found something very interesting about these three different polyelectrolytes. We found that the outer layer can steer the nanoparticle to different parts of the cell. Hyaluronic acid, for example, tends to accumulate in the endosome of these cancer cells, and we can see them in the middle of the cell. This is something that we understand is taking place through receptor-mediated uptake through the binding of the CD44 receptor. However, polyl-glutamic acid is quite different. These outer layers traffic to the outside membrane of the cell, and they tend to remain there for extremely long time periods. We have actually observed up to 5 to 7 days. Polyl-aspartic acid, on the other hand, has an in-between behavior. It internalizes, but very slowly. So the nanoparticles exhibit an affinity for the surface membrane, but over time, they get taken up very slowly through a different process known as essentially caveolar mechanism. So we have these three different behaviors with these different cell types. And we're asking the question, how can we apply these formulations to specific drug delivery applications? Hyaluronic acid internalizes quickly, and this is a way of getting intracellular delivery of nucleic acids and small molecules into the cell where we have the action. Polyl-aspartic acid has a very slow internalization and has some residence time on or near the cell surface, and this may be interesting for a kind of staged release or stimuli responsive release. Polyl-glutamic acid, however, has a prolonged surface retention. This means that the nanoparticle sits on the outside of the cell and never goes inside. This is actually interesting because it gives us an opportunity to deliver proteins to neighboring cells, in particular proteins that would normally get broken down if they went inside the endosome where the pH gets lowered. And this gave us the idea that we might actually be able to use this application to create hot tumor environments. And to explain, there's been a strong interest in immunotherapies that can be used to treat cancer. And the idea is to activate the immune system against cancer cells. However, immunotherapy approaches have only worked for a relatively small fraction of the cancers that humans experience. One of the reasons for this is that there are a number of tumor microenvironments in which the immune cells that are the actors in upregulating the immune response are turned down or turned off. Now, there are many ways in which we can try to use inhibitors to address some of these modes of immune suppression, but there are other types of immune suppression that are not responsive to those inhibitors. And we found that ovarian cancer, especially the most aggressive forms of ovarian cancer, are highly non-responsive to current immunotherapy treatments. However, one way of activating the immune response is to deliver cytokines directly to tumors. And these cytokines are small molecules or proteins that signal to the rest of the innate immune response. And the one that we decided to look at was the cytokine IL-12, which is a simple 70,000 molecular weight heterodimer protein. IL-12 is actually able to activate T cells and NK cells directly. And when it does that activation, it stimulates the generation of interferon gamma. And interferon gamma is one of the primary immune regulating molecules. It enhances T and NK cell activity. So here we can see some of the cascades that we get from IL-12. And normally IL-12 is generated by activated dendritic cells or other macrophages. However, in immune poor environments, we don't have as many of these cells present. So the idea is that we might be able to deliver IL-12 and activate these neighboring cells. The problem is if you deliver IL-12 directly to the body, it's extremely toxic. There are a number of off-target effects that we can get from the immunological response. So we want to avoid that as much as possible. This is actually a treatment that has failed in clinical trials in the past due to the systemic effects. You essentially activate the immune system to act against itself. And this is something that can cause a huge amount of death as well as other side effects. So we want to avoid in vivo toxicity, and layer by layer nanoparticles can provide us with that opportunity of both targeted delivery and protection of the IL-12 interactions with healthy cells. So here we're looking at our particle toxicity reduction, comparing the body weight of mice who have been treated with IL-12 in its soluble form, shown here in blue. And over a period of days with this treatment, we see that they're losing a huge amount of weight, and at this point are getting close to that weight where we have to sacrifice them. However, we find that in our encapsulated nanoparticle formulation, which is shown in the light color here, we don't see any of this loss of body weight, and we get something very similar to the PBS control. We also can see that the amount of that cytokine that is present in the serum is different when we have the free IL-12 present. As shown here, we have a lot of it that is being picked up in the bloodstream where it can actually induce a cytotoxic effect. However, that concentration in the bloodstream for our encapsulated particle at moderate and higher doses is very low. When we first tested this IL-12 nanoparticle, we looked at colon cancer because it was a simpler and more responsive kind of cancer to examine. And we found that indeed we could deliver large amounts of IL-12 to the animals in our nanoparticle form and maintain the efficacy of the IL-12, and in fact, perhaps extend it because we could increase the dose significantly. So here we can see the extended lifetime that we can achieve. We found that this IL-12 therapy also enhanced T cell activity. It's important for us to understand whether or not we are impacting the immune system in the way that we think we are. And it turns out that indeed, in our nanoparticle is able to give us very similar kinds of CD8 positive T cells as the soluble IL-12. We also see that the fraction that is present in live cells is similar. And when we compare CD4 versus CD8 cell populations, which represent essentially the number of activated immune cells that are able to attack the cancer, we find that, again, we get similar results to if we had introduced the IL-12 directly, neat. But what was really exciting to us is that this also works in ovarian cancer. And we have a very nice demonstration of the fact that with this 5 microgram dose, we can actually extend life. In fact, it's a little bit easier to look at the relative toxicity in the same animals. For a 10 microgram dosed healthy animal, we see that there's significant death. Whereas with the IL-12 nanoparticle, we see that we don't have this death that is taking place and this huge loss in weight. The arrows here indicate animals that were sacrificed because they lost significant weight. When we do the study with survival, we can look at a control and see that these animals die very rapidly without any treatment. When we treat with IL-12 in its neat form, we can extend the lifetime, but all of the animals ultimately die, and they die fairly early. Compared to the treatment with our IL-12 nanoparticle, in which we see that we have not only extended the average life survival time, but we have mice that are continuing to live out to 200 days. So we've been excited about the fact that we can address immunotherapies using these nanoparticles. The outer layers are actually very practical for attachment of other ligands. So in a collaboration with Sangeeta Bhatia, we decided to combine the ability to deliver with the ability to detect and monitor disease. In this study, we used an siRNA-loaded therapeutic LBL nanoparticle, in which we have an siRNA that is designed to essentially knock down some of the tumor mechanisms for ovarian cancer. And we have a targeted theranostic LBL nanoparticle that contains this clicked-on group. And this clicked-on group is actually a urinary biomarker that is cleaved by the enzymes that are present in the cancer. The more enzyme that is present, the more of this marker that comes off, and it can be measured because of its high molecular weight as a biomarker in urine. So we've already described the layer-by-layer nanoparticle. What we added to this was these functional molecules that could be attached to the free acid groups. We actually designed a propargyl-modified poly-L-aspartic acid so that we could use click chemistry to attach them. And we added these tumor-targeting ligands, which are cyclic RGD, and allow us to have a more effective tumor penetration. Finally, we began to look at how the additions of these different ligands changed the intracellular trafficking of our nanoparticle. And we found that indeed, when we have the unclicked nanoparticle versus the nanoparticle with IRGD, for example, we can see a very significant difference in the net rate of uptake and accumulation inside the endosomes of these cells. We're also able to confirm the diagnostic function in vivo. by looking at the accumulation of these nanoparticles in tumors of various types, everything from pancreatic to colorectal to ovarian cancer. And we were able to see that we have this upregulation in signal in both flank tumors, metastatic, and orthotopic tumors. And this is exciting to us because it indicates that consistently we're able to detect the presence of the cancer as well as introduce the treatment. The idea then is that we would be able to, in a continuous treatment process, monitor the progression of treatment over the period of weeks and months and determine whether or not we have an effective decrease in that signal. We've also been able to confirm the knockdown of genes in vivo. Here we're showing a 50% knockdown of luciferase at day 3, for example. And we've actually moved on to look at siRNA treatments and work that is about to be submitted for publication. So I'm actually going to end with a different topic. And this is actually a different kind of nanoparticle, which is used to address osteoarthritis, but follows the same theme of electrostatics to treat disease. In this case, though, we have the challenge of penetration of nanoparticles into cartilage. And there's a reason why this is a unique problem. First, it's worth mentioning that osteoarthritis can take place through an early lesion or injury to the bone or cartilage. And that ultimately leads to degradation of the cartilage over time due to excessive inflammation. So we can actually use oral steroidal drugs, corticosteroids, for example, and all of these tend to treat the inflammation that occurs at the early stages and pain, but it does not get rid of the osteoarthritis state. And then on the other end, when we get to degradation that is too extreme, we have a surgery and a joint replacement. But there's actually not a disease-modifying drug that can stop or slow the rate of degradation of cartilage. It does turn out that there are proteins that we know will help to stimulate the generation of cartilage. And these proteins are typically growth factors. However, if you try to inject these growth factors into the joint space, what we find is that those proteins have difficulty penetrating and reaching the cartilage for significant amounts of time. And the problem here is that we don't have any blood vessels in cartilage. So unlike the previous problem in which we could take advantage of nanoparticles accessing the bloodstream, here we don't have any route that takes us directly to the chondrocytes or cartilage cells that exist in this cartilage matrix. And cartilage is truly a matrix. It actually consists of very highly negatively charged proteoglycans, which are really these bottle brush-like polymers that have polysaccharides that extend out and give us essentially this very nice brushy, strong network. But this network, which is essentially a gel, has a very small mesh size, typically thought to be somewhere between 10 and 20 nanometers. And it's very difficult to get a particle through this very dense and very highly charged mesh. So we have two things at play here. We have charge that we have to deal with, and we also have mesh size. And it turns out that the only way into cartilage is to have something that is positively charged, but also small enough to penetrate. So we know from a series of design studies that small is best. We also have the issue of binding and uptake. And in this case, if something gets into the cartilage, it can also be very rapidly flushed out because there is a lot of flux that takes place in the cavity of the joint. And this leads to rapid clearance of molecules that are introduced into the region of the joint. and exiting of those nanoparticles through lymphatic vessels and venules. So nanoparticles that are introduced in may not hang around for a long time because there is this constant and rapid clearance. So we need something that is going to get into the cartilage and then stay there, stick for long enough that the IGF or growth factor can signal to those cartilage cells or chondrocytes effectively to generate new cartilage. So I'll briefly describe two different ways in which we approach this problem. One was the generation of a nanoplex or a complex coacervate, and the other was the use of a dendrimer. When we first began this work, we started by taking the idea of layer by layer to the level of a polyplex. And the idea was to take IGF, which is the growth factor that is going to be our therapeutic. It has a net positive charge because it has an isoelectric point of 8.5. We can essentially wrap it in poly-L-glutamic acid. And then, after we have created that complex, titrate in poly-L-arginine. So we have a two-step process. And we create this, essentially this layered complex. We found that when we did a simple treatment in a surgical rat osteoarthritis model, our nanoplex performed very well compared to free IGF. Here we can see the cartilage is stained in this red color. When we do the surgery, we actually damage or remove some of that cartilage. And when we introduce the treatment, we look for regeneration of this red tissue. And we find that this actually was effective, but we had a problem with it. We found that the reason that these complexes worked was because they tended to consist of larger complexes that broke down into smaller ones, so that we had essentially an average size of these smaller complexes of about 16 nanometers and a charge of about 50 millivolts. However, it was not clear how much of the IGF was getting into the cartilage versus remaining in this aggregate form. On top of that, any attempts to modify or add to this formulation tended to lead to precipitation. It's very difficult to maintain the stability of this form of nanoplex when we want to introduce any other additional chemistries. So we moved to a more systematic way of addressing the issue. We chose to work with polyamidoamine dendrimers, and here you can see an example of a PAMAM dendrimer. These are very uniform. They have a known size, and they have a known charge density based on the primary amines. So we have these primary amines available to provide positive charge, but they also serve as very useful chemical handles for attachments. If we actually look at a PAMAM dendrimer, one of the first things you think of is the fact that you have to deal with toxicity, because these highly positively charged molecules can actually interact with and blast through a range of different cell membranes. So we have to control the toxicity by controlling this charge density. There's also an additional issue, which is that if we have all of this charge present along the perimeter of the molecule, it will become too highly charged to actually advance through a strong negatively charged matrix. It will actually bind to and be kinetically stuck at the cartilage surface for long periods of time, longer than the treatment time that we're interested in. So the answer to this was to introduce polyethylene glycol chains to a certain portion of the molecule and have the remaining amine groups retained. This allowed us to provide a balance between a positive charge and polyethylene glycol, which can shield that charge. Therefore, when the PAMAM dendrimer is introduced, it can actually have these modulated interactions. And depending on the relative degree to which the charge is shielded, we should see a decrease in toxicity. We can then attach our protein, our therapeutic protein, to one of the free amines on the PAMAM dendrimer, and we have a carrier that can bring IGF closer to the chondrocytes. So we actually looked at an entire panel of pegylated dendrimers and varied them by size and by density. And we looked at the ratio of in-group pegylation for all of these systems, both for generation 4 PAMAM and a slightly bigger generation 6 PAMAM. And what we're looking at here is the degree to which the polyethylene glycol chain overlapped with neighboring chains. And we found that there was an optimal charge by which this fractional in-group pegylation was very effective in providing just enough of the steric charge reduction to give us what we wanted. And what we wanted was deep penetration into cartilage. As we can see here, we used a fluorescent dendrimer bath, and we looked at how much of the dendrimer actually penetrated into the cartilage disc in these time studies. And what we found was that this optimal regime could be understood by understanding polymer brush physics. If we were able to introduce the PEG chains in ranges that went from essentially a sparseness, which exposed free charge, to a point at which we get a little bit of overlap of the PEG chains, to a point in which we have the PEG chains very densely packed, we found that the best uptake combined with the most reasonable viability happened in this in-between zone, where we have somewhere between the density of overlap to twice the density of overlap. And we found that under these conditions, we got a greatly enhanced penetration, in particular with generation 6. Here we can see that generation 6 with 45% PEG gives us extensive penetration. And we can see this in these markups here, in which you can see a very significant amount of uptake as you go from 2 days to 6 days. So this is the formulation that we used in our studies. And we found that in an intra-articular injection of a rat in which we have introduced damage to the cartilage, we can see that the IGF-1 alone is going to get cleared over a fairly short period of time. But our pegylated system with the IGF-1 remains for much longer time periods. And in fact, we see that we've increased the half-life of the IGF-1 by an order of magnitude. So we go from a half-life of less than a day to a half-life of over 4 days. And the period of time that the concentration is therapeutic is much larger. So it turns out that the therapeutic time for the free IGF was just over a period of 1 to 2 days. However, for our generation 6 dendrimer dose, we found that we had therapeutic concentrations all the way out to 30 days. This is key because it's thought that these kinds of intra-articular treatments should only take place on a monthly basis. And when we look at the cartilage regeneration, we see that here we have a no treatment case where we have removed some of the cartilage or damaged it. And we have the healthy rat cartilage. If we look at treatment with just IGF alone, we see there's only been a bit of recovery. We compare this to our treated animals, we saw that cartilage was regenerated consistently in these regions. So I've talked about how we can use nanoparticles and electrostatics for a range of different treatments, how we can design them so that we have synergistic multi-drug release. And we actually find this is an incredibly versatile tool that allows us to use both specific and non-specific binding interactions to target specific cell types. Right now, we're working with systems biologists to understand some of the interactions that I talked about and use them to target specific tissues and cells. For example, we're looking at the design of layer-by-layer nanoparticles, which might be able to target inflammation in lungs, of infected humans. In other words, when we get an infection that exists in the lung, like COVID-19, or a range of other known infectious agents, we get huge amounts of inflammation. And we believe that we can use the same sorts of targeting tools that I described here for cancer to be able to target our nanoparticles to inflamed tissues and deliver therapeutics such as dexamethasone and other corticosteroids to the lung, and an approach that would allow us to address a number of the symptoms that lead to death in COVID-19. We also believe that these kinds of tools can be used for very effective release of vaccines. And we've been coating microneedles with layer by layer films that allow us to essentially design a vaccine from the bottom up and deliver it directly to the skin. So I'll stop there and thank the students who did the work, including those highlighted in bold, and the funding agents, and welcome any questions. Thank you.
Thank you so much, Paula. I will go ahead and share my screen. We have a series of questions for you that have been coming in. There we go. So first, for the in vivo study of tumor treatment, the results are very impressive. For the penetration, can you explain how it happens? Is it physical or chemical? And can it be controlled?
Those are great questions. For the tumor penetration of these highly carboxylated nanoparticles, we believe this is a physical diffusion. We know that when we use hyaluronic acid or polyaspartic acid, that there's not a very specific chemical interaction with tissue. In fact, these are polyelectrolytes, such as hyaluronic acid, make up a part of the interstitium or tissue. So we believe that these are facilitated by, in part, the fact that we have these high levels of hydration around the nanoparticle, which may be able to facilitate the transport of these nanoparticles. There may also be additional factors that have to do with the ability of these very charged nanoparticles to penetrate the tissue. But we haven't done the studies which we hope to do in the future, which can indicate what those differences are. We have found, I should mention that there's a biological aspect as well. The HA nanoparticles penetrate further than the polyaspartic acid ones. And we think that's because they actually do bind to CD44, and that may be facilitating transport of the nanoparticles either through transcytosis or in some form of endocytosis, and then passing on that cargo.
Okay. The second question, dear Professor Hammond, a very impressive talk. I'm wondering, for the less toxic encapsulated nanoparticles, what is the size dependence of the nanoparticle, and does it affect the results and lifetime of the particles?
Yes, that's great. The smaller that we can make the nanoparticle, the longer the half-life that we can achieve. And this is something that's generally been observed in nanomedicine, especially if we have an effective outer layer. However, we have found that for our particles, which are larger, maybe about 100 nanometers, we can still get something like a 28-hour half-life with a very dense hyaluronic acid or very dense negatively charged corona. But yes, nanoparticle size definitely affects these results. And when we were working with smaller nanoparticles, for example, we coated gold nanoparticles and quantum dots, we could get even more extended half-lives.
Mm-hmm. The next question up is, how do you balance the stability of the layer-by-layer nanoparticles outside tumor cells versus efficient decomposition inside tumor cells? Or inside tumor cells?
That's an excellent question. We're actually we have been studying this for the last couple of years, and this is one of the focuses of our current work. But it's possible to design these layer by layer systems so that they form a very stable ionically cross-linked network at pH 7.4. And often you do this by choosing your process conditions. However, you can design them so that when they are introduced to a lower pH environment, such as 6.5 or 6.0, you begin to eliminate some of those charged groups. And the layer by layer film undergoes essentially a restabilization, and that can lead to swelling. And in some cases, we can design these systems so they completely fall apart. So I didn't mention it, but in the case of the immunotherapy nanoparticles, we actually have an outer layer that is designed to fall apart in the tumor compartment at this slightly lower pH. And we can actually measure the rate at which we shed the layers. And this is because of a very slight shift in pH. So you can absolutely engineer the stability so that you have a system that's stable at one pH, slightly unstable at another.
And actually, a related question then, are there other places that are a little more acidic in the body that one sees effects by making those nanoparticles sensitive to the pH?
If you're looking at pH sensitivity, the other cases where you might see a lowering in pH is any place where there's inflammation. So this would typically work well if we were treating a cancer patient and the cancer was significant enough that you were beginning to see hypoxia. But we actually think it's even more effective for targeting inflammation because in those cases, we can actually see some of the same kinds of effects in highly inflamed tissue. In terms of other areas, typically in a healthy human, there are not areas that we would see in the typical blood from access through the bloodstream that would have a lower pH though. And I should also mention that enzymatic decomposition is another area that we've been interested in, and it has similar advantages.
Very good. And then the next question is, what amazing work using nanoparticles for OA. I've suffered with this problem for many years. When might this method reach the clinic for real treatments?
I'm really excited about the OA work too, actually. In our lab, we just received a grant from the DLD that is meant to help us with translation. And in this work, we're going to be doing veterinary dog studies in which we will be treating dogs with arthritis. So that would be the first step. And that will take about 2.5 years. I think if we're able to see success in the vet studies, the idea would be to get a partner that can work with us for human clinical treatments. So the hope would be this could even be within 5 years, but that all depends, of course, on creating the right partnerships that would like to invest in these studies.
And that brings up another question that came in a little too late to put on the slides, and that is, can you tell us something about the crossover in your laboratory? You target these different diseases. First, how do you choose them, and how much overlap is there? Is it that you see that a method that you've applied in one disease may be applicable to another, or you take on a disease that you see as needing treatments? How does that work when you run as broad a laboratory as yours?
That is a great question too. There are actually a combination of things that determine the areas that we work on. The work that we're doing on cancer is something that originated because I had a strong interest in developing our materials to address cancer. I had a strong interest in addressing that disease type. However, we also have projects that have been focused on bone, for example. And that work, which was really inspired by the fact that we had this very nice sort of sequenced way of delivering growth factors, led to conversations with clinicians. And a range of them said this would be really interesting for the delivery of bone-related growth factors because the rate of release and the amount released these are some of the limitations that we have in the field. So it was really by talking to other clinicians that we began to work on bone regeneration. And when we began to work in that area, my own students began to talk about cartilage and soft tissue. And this is how we began to investigate cartilage. So it really is a combination of personal motivation, engagement with others in the world who really tell you where the problems are and what we should be working on, which is key. And then inspiration from the members of my own research lab who are similarly triggered by what they're reading and what they're understanding about problems in the world.
Fantastic. I remember so well visiting you, and you described, we were outside of your building and you describing how you were going to go immerse in medicine to learn what problems you could address with the tools you had and the ones you developed, and you're about to take a sabbatical at the hospitals in Boston to go learn enough to do some good. That was that meeting really sticks in my mind from I guess a few years ago now. Well, you've come so far.
Right. Exactly. I was getting ready to immerse myself in Dana-Farber Cancer Institute. And yeah, that was an incredible experience. I learned a huge amount about the problems, very real medical problems. And I also learned what to not focus on. And that was equally important for me.
Yes, I think maybe that's it. That's a good segue into where we'll go in our panel in just a moment when we bring Andre Nell on board with us. But first, let me, in real life, this would be bringing a plaque across the stage to you and thanking you for this wonderful lecture. For now, we have to settle for the electronic version of that. So on behalf of Professor Alice Shang at Beida and me and this very broad audience around the world that we have, thank you for connecting the world together in science, and in particular the polymer work that you brought together in your laboratory to do targeted delivery in medicine, and for this fantastic talk that you shared with us. And we very much appreciate it. And now what we'll do is we'll pull our next speaker, Professor Andre Nell, on stage. I'll give him a formal introduction before his talk, but for the audience, let me just say that he's the founder and chief of nanomedicine at UCLA, and he's also editor at ACS Nano and also a top clinician here in the David Geffen School of Medicine and our Ronald Reagan Hospital. And so welcome, Andre, and here we are. Okay, so what we try and do in the panel is give a little more insight into how we choose our science. We heard a little bit about that at the end of Professor Hammond's talk, and in particular in this time of COVID, we're interested in, and I think the audience is generally interested in, how work has changed and been redirected, and what maybe special opportunities there are given our backgrounds. And I should also introduce, Professor S.K. Ramesh of Cal State Northridge, who will be speaking at the end of the program today. He's one of the candidates for IEEE president. You heard from another last week, and so he'll tell you a little bit about his engineering expertise. So I promised not to give him an examination on medicine, but certainly things have changed in universities and administration and engineering for him, and so we'll also pull him into this discussion. But maybe, Andre, let's start with you. You've you've put together a very active program in COVID research. And can you tell us something about the bridge from what you were doing previously into this effort that we're about to hear, what we'll hear in the next hour?
Thank you, Paul. I hope you can hear me clear enough.
Yes.
Okay. Thank you for the kind introduction, and thank you, Paula, for an excellent talk. So I am a clinician who studies allergy immunology, got interested over time in research on air pollution in Los Angeles, of which we had certainly had a lot. And from there segued into the discovery that the most dangerous air pollution particles are from car and vehicular emissions, and those are particles in the nanoscale range. And so, with the advent then of nanotechnology in the early 2000s, we were very interested that you could engineer a particle rather than getting a particle that is emitted and thrown out at you. And from there, segued into bringing nanotechnology into our research, and we covered various different areas, but essentially became interested on one side on the safety of nanomaterials, for which we got a large national center, and then on the nanomedicine side, very interested in cancer treatment, drug delivery, and that's evolved also over time because I'm an immunologist into cancer immunotherapy, and most recently also being able to use nanomaterials for applications for COVID vaccination.
And did you transform your laboratory over to focus entirely on COVID, or have you kept up some of the earlier work during this time?
No, I would say, Paul, at this stage, a very small part of our laboratory is tied to COVID, where actually the nanoparticle vaccines are coming from that we are developing for COVID is from the cancer treatment, as I will try to demonstrate today, as well as nanoparticles that intervene in treatment of autoimmune disease and allergies. Those are particles that we've made that are targeted to specific aspects of the immune system to change the direction of the immune system. And so we use that basic design concept and also to bring it to COVID. And I will show, I have very little that we've done on COVID so far, but with the challenges out there today, I will try and outline how we can, develop more and more applications in this area.
Very good. And Paul, let's go back to you. You teased us a little bit that some of the particles you were making would address COVID and the lungs. Might you expand on that a bit?
Yeah, so we're also at the very beginning of examining this, but we have been designing nanoparticles in a collaboration that is part of the Singapore-MIT Alliance for Research and Technology, or SMART, which would be able to target biofilm in the lung or would be able to target inflamed regions of the lung. We're looking at both ideas. And the idea is that we can adjust those outer layers that I talked about so that they are responsive to inflammation, either through an enzymatic transformation or through a pH. And it's also known that in inflamed lung, you have also some of this permeability or defects in the blood vessels that are a result of that inflammation. So nanoparticles are an ideal approach to try and address that. So we're beginning to take a look at that. We're looking at the incorporation of antibiotics for the work in Singapore. And at MIT, we're beginning to think about how we might be able to incorporate anti-inflammatory drugs, because it turns out that for really advanced infections that lead to the kinds of respiratory distress that we're concerned about, inflammation is one of the key players. And if we can turn that knob down, we can perhaps save lives. So we've begun to look at this. This is really on the level of, I have a student who's working on some of these ideas now, and we're putting together those early seed grant applications. So we're excited about the idea of moving this work forward to address this disease.
And Andre, maybe let's swing back to you for a second. Are there some special properties of the parts of the lungs one would want to address when there is infection and inflammation? Is the cyclic turnover with breathing of the layers significantly different in a way that one might use to advantage in treatments?
Well, there are, from what Paula has just said, there are two ways to approach the lung. The one is, of course, you can send stuff to the lung via the systemic circulation. And so that's an intervention type where you normally would use particles that can withstand systemic spread, can target in on the lung, etc. The other side of the story of the lung is, of course, to try and get nanomaterials that you inhale or through aerosolized inhalation into the lung, and where the design of those materials need to be very, very specific, because there is a size restriction for particles that enter the lung, and you have to design your particles exactly in order to decide where in the lung you want to enter. Once you have made that decision, then of course an important consideration becomes the delivery system that you use, because nanoparticles can easily be aerosolized, but if you want to deliver it as the powder, you require a lot more force. When you decide that you want to intervene in bacterial forms or infectious disease environment, a lot of design characteristics has to go into the nanoparticle being able to penetrate into those bioforms, because they present, other than the infectious material, quite a challenging environment in order to engineer your way into actual delivery and intervention into what you want to do in the bioform. So perhaps Paula can elucidate more on that.
Yes, absolutely. And Andre really draws a nice picture of the two different design approaches and criteria. When we are looking at biofilm penetrating nanoparticles, these are systems that we would ultimately need to design so that they could be aerosolized. And in that sense, we would be working with collaborators. But we've been looking at how we might be able to adapt the exterior of a nanoparticle so that it undergoes shifts in charge or charge density, taking advantage of some of the same ideas I described for penetration of cartilage. However, biofilms are different in that they are a sort of dense mess of DNA and proteins that give you a fairly difficult net to get through. So we're looking at ways in which we can cleverly design nanoparticles so that they slowly undergo a transformation in their outer layer to become more and more actively engaged with the biofilm, so that we can get deeper penetration into that film. Biofilms tend to enable bacteria to exist in a more dormant form. In that form, antibiotics alone are not necessarily as effective, because bacteria aren't metabolizing the way they would if they were active in the fully active state. So along with designing a nanoparticle that can penetrate, we also have to be clever about what we're going to deliver into that biofilm that will be effective against bacteria. And there are collaborators in Singapore who have looked at a range of different extremely effective antibiotics, as well as dispersal agents, which tend to disperse or eliminate the biofilm. And I think these are the directions that we need to go in if we're going to try to approach the biofilm directly.
Thank you so much. Let me bring Professor Ramesh in. I'll use the tenuous segue of engagement. So Professor Ramesh has been in university leadership positions at a couple of different Cal states, and this is a time when our students are remote, our colleagues are remote. We have to figure out how to work together and change how we teach classes, do our establish interactions with students and colleagues. Can you say something about how you've done that, and also for the professional society point of view at IEEE, you have several 100,000 members around the world, how one does that without being able to travel or meet in person. And I'll put Paula on warning that I'll come back to you as department chair in Chemie, because I know from engagement with you that's been that's been quite a burden. So maybe let's start with Professor Ramesh. Welcome.
Right. Thank you so much, Paul, and good morning, good evening, wherever you are. I want to thank you and Alice for the opportunity. Professor Hammond and Dr. Nell, just listening to both of you, the thought that comes to mind, all of you, is a line from the National Academies of Engineering in the United States that said, "No profession unleashes the spirit of innovation like engineering." Truly, not to be cliche, but I believe that engineering is a Renaissance degree discipline of our disciplines of our times. As I listen to you about treatments for nanotechnology, as I listen to you about the things that you're doing at the cutting edge that have a direct and positive impact on people's lives, that's what we do as engineers. We're creating products, processes to enable a better quality of life for everybody on the planet, including us, the engineers. So as an educator, as an engineering educator, to me, access is very critical. So Paul, you raised the question about how we're dealing with the situation right now in the California State University system, which is the largest public university system in the United States, where 500,000 students, 50,000 or so faculty. We entirely pivoted on the 12th of March to go virtual. And what I'm most proud about is the persistence, the grit, the determination that our students and faculty have demonstrated during this time of challenge. A lot of them don't even have access to proper housing. There's housing insecurity, food insecurity, and above all that, they're studying all these remarkable disciplines. Build Pader, which is a great program that we have to train future biotechnology students. The AIM Squared program that I'm reading, Attract, Inspire, Mentor, and Support students with the Department of Education, supports first-generation students who are first in their family to go to college. And I've really learned a lot listening to my students during these challenging times. What I would say, the role of professional associations like IEEE at a time like this becomes incredibly important, because the IEEE is about 400,000 members strong around the world. We have 46 different technical societies and councils, and yes, everything from the BRAIN Initiative to autonomous systems and ethics. It's truly, truly important for us as engineers, not only to design these future systems to help humanity, but also to be very mindful of the impact it has, the ethical impact that it has. So we're trying to teach all of those things, and by the way, learn those things along the way. And let me close with just one line here, Paul. It's my favorite poet, Maya Angelou, and she says, "We may suffer many defeats, but we must not be defeated." And listening to my colleagues, both Paula and Andre, I'm inspired. I'm inspired that the future holds so many possibilities for us, and I look forward to sharing some of that during my presentation a little bit later. So thank you.
Thank you very much. And Paula, as head of the chemical engineering department, when the world turned upside down very suddenly, can you tell us something about what that was like from your perspective, and how how we've proceeded, and maybe where we are in this transformation?
Absolutely. It was really an incredible moment when we saw universities shutting down, when we saw students being sent home, and it definitely had an emotional toll on all of our community. to have to give up the thing we've treasured most, which is to spend time together, working together, elbow to elbow on important problems and learning together. So certainly in my own community at MIT, there was that sense of rush and concern. And, it took us a little bit to really stabilize from that. But after a few weeks of very careful and measured response, we began to really talk about how we could do our research from our homes, how we could think more deeply and broadly about our work while we were grounded. And that led to some very interesting developments and new ideas that I saw popping up from many different research groups, both locally and around the world. And as we began to phase ourselves back into research, there is this ability, I think, we're so resilient to come back 100%, to embrace what we have. And even though in the beginning, many of us had limited hours in the lab, limited time frames, we embraced what we were doing and in fact loved it even more for the fact that it was precious. And I have seen some amazing things. What really struck me during the time that we were almost practically shut down, MIT was ramped down to only the most critical experiments and COVID-related research, was that I had colleagues in my department who were working on critical applications of their work. A member of our department who had developed a very rapid way to scale up vaccine manufacturing began to really move forward with his efforts with a Gates Foundation grant. Another colleague of mine who she had developed a very rapid assay that was very reliable, and she was able to advance it both in Singapore and in the United States with a partnership with 3M to create a paper diagnostic, which we hope we will see continue to move along with the RADx set of diagnostics. So just watching my colleagues putting in all of this effort, going into lab, even when there was some uncertainty about the risk, being very careful, but putting in that time made me admire my colleagues even more, both at home at MIT and across the world. I saw this kind of activity and it was incredibly inspiring. I think that as we began to get our pace again, even in this very cautious world, although we miss each other, we find ways to encourage each other, to rally each other on, to reach out and to build new ties. And I think that is the essence of science. We find each other, we find a way to talk to each other and share ideas. I am very happy for the fact that we still have an ACS meeting that happened. We still are planning to have American Chemical Society, I should say, the American Institute of Chemical Engineers, and there are many, many other organizations that have reached out and helped us maintain some level of connectivity so that we can share our stories with each other.
Is there something that you have seen that you'd like to carry forward when the world opens up again that's been advantageous?
Definitely having a virtual platform means that more people can attend. So I think although we still need to have our in-person meetings, having some elements of our meetings be virtual is not a bad idea. It means that when the ACS meeting is in a place that not everyone can reach, if we have some of our plenary sessions or some sort of critical cross-sectional session that is done in a virtual format, even within the context of the in-person meeting, I think we could get a lot out of it. I found that even faculty meetings are better attended when they're virtual. So
we have also found that seminars and faculty meetings, yes.
Yes, attendance just jumps up. So I think that we need to leverage that in some way.
I agree. And Andre, let me return to you. You're in a hybrid position really in the School of Medicine, where you work side by side with clinicians who will be on the front lines. You're a clinician yourself. And then there are the, not just responsibilities, but opportunities in research to take, what's being learned in real time and translate it into treatments that can address the pandemic and the patients who are, right there in the same building with treatments. Can you say something about how the environment changed, and if there's some, if there's something that we might learn and carry forward?
Well, I think, Paul, that with the advent of the pandemic, of course, where people, stayed home and quarantine, that a huge development was to deliver healthcare by what Paul had just mentioned, being able to do it via remote communication, Zoom medicine, if you want, in order to conduct clinical care. And while it took a little bit of time for that to come forward, the technology is now well established, so that in the middle of the COVID pandemic, a lot of medical consultation is done remotely. The other part that has changed, I would say, dramatically is the awareness then of intervention in an infectious disease. And whereas, viral diseases and respiratory diseases have been commonplace treatments in medicine, the new challenges that came from a virus like COVID meant that a lot of innovative research had to be undertaken. And we basically busy rewriting the book every day. For instance, in the talk that I will give today, more than 90% of the publications that I will be talking about have all been published in the last 3 months or still have to be published. The areas that the research have gone into is unbelievably wide applications, from antiviral therapies to systemic drug delivery to deal with systemic inflammatory syndrome. And then, of course, what I will highlight today, the major role of nanotechnology in assisting a new type of vaccine development, very different from vaccine development that we have done so far. And what I think is will happen as a result of the outcome, many new technologies for vaccine delivery will emerge from here based on the discoveries that was made now in the COVID era.
Very interesting. So maybe good news for textbook publishers. Those will be rewritten, and maybe on the panel we could take a vote where the yet to be published best papers should be sent for submission. Laziest nano in joke, 3 of our editors up here. Anyway, well, thank you very much to the panel for a most interesting discussion, and I'll put in a plug for the for a panel coming up in November, in which we'll look at how COVID has affected different aspects of science and engineering and medicine, as well as our connection to society. We'll have some of the leaders around the world of both scientific societies and national academies to talk with us. So stay tuned for that in November. And now it's my very great pleasure to introduce my colleague and friend, Andre Nell. So Andre is a distinguished professor of medicine and is the founder and chief of the Division of Nanomedicine at UCLA. He's the director of the University of California Center for Environmental Implications of Nanotechnology. As you've already heard, he's one of our editors